Welcome to the Explainer. If you've ever looked at Go code and just felt completely overwhelmed by all those asterisks and ampersands floating around, you are in exactly the right place. Today, we're going to completely demystify Go memory addresses, and we're going to do it together using simple, everyday analogies. Think of me as your personal tutor. By the end of this session, you won't just understand pointers, you'll be able to picture exactly how they work in your mind. Let's get started.
So here's our game plan for today. We'll start with our core analogy, pointers as sticky notes. Then we'll put that to work delivering answers with our divmod function. Upgrade things in place with Ultimate divmod and test out a simple remote control concept with point 1. After that, we hit the boss level with pointer inception in Ultimate point 1 before finally comparing all our tools.
All right, section 1, pointers as sticky notes. Let's lay some groundwork.
Okay, let's dive right into this fundamental concept. When you create a standard variable in Go, say an integer, I want you to imagine a physical, literal cardboard box holding a number inside. So what is a pointer? A pointer is simply a sticky note. It doesn't actually hold the number itself. Instead, it just has directions written on it, telling you exactly where to find that physical box in the giant warehouse of your computer's memory. And creating that sticky note, that's exactly what the ampersand does. It writes the address down for you. Once you have it, you'll encounter that intimidating asterisk symbol, the one we call dereferencing. Honestly, that's just the action of following the directions on the sticky note, walking right up to the physical box, opening it up, and interacting with whatever is inside.
Moving on to section 2, delivering answers with the divmod function. Let's see these sticky notes in action.
Let's look at a real Go function from our source material called divmod. This function has a specific job: perform a standard division and figure out the remainder. It takes 4 arguments. The first two, A and B, well, those are normal integers. These are your standard boxes. They hold the actual numbers we want to divide. But look at the next two, div and mod. These are pointers. We're essentially handing the function 2 sticky notes. Why? Because the function needs to know exactly where to deliver the final answers so the caller can actually find them later.
Here's how it actually plays out. Step 1. The function does the math, calculating the integer quotient of A divided by B. Step 2. It calculates the remainder using the modulo operator. And now for step 3. Look at the code where we have asterisk div equals A divided by B. Think back to our analogy. The asterisk means we're dereferencing. We are following that div sticky note to a specific box, and we're placing our quotient directly inside it. And we do the exact same thing with the mod sticky note. We didn't just calculate an answer. We literally delivered it right to the caller's doorstep.
Next up, section 3, upgrading in place with Ultimate divmod. Time to level up.
Now, what's really interesting here is this concept of in-place updates. Our new function Ultimate divmod doesn't even take separate variables for the answers. It only takes 2 pointers, asterisk A and asterisk B. It's kind of like renovating an existing house instead of buying new land and building a whole new house just to store your furniture. We're going to calculate the division and remainder and then write those answers directly over the original input values. It is incredibly efficient because it saves memory.
But there is a little catch. First, we have to calculate the quotient and remainder and store them in temporary variables. Why? Well, imagine you're renovating that house. You absolutely wouldn't tear down the walls while you're still using them to measure the room's dimensions. If we overwrote box A with the quotient right away, we'd lose the original number we still need to calculate the remainder, right? So we measure everything, keep the results safe temporarily, and then we dereference asterisk A and asterisk B to update those original boxes with the new values.
All right, section 4, the remote control. Let's explore the point 1 function. Before we hit the absolute boss level, let's look at a simpler, more direct example to really cement this indirect modification concept. Meet the point 1 function. Think of this function as just a basic remote control. We pass it a single sticky note, a pointer to an integer, and its only job is to push a button that changes the value in that distant box to exactly 1. The process is incredibly straightforward. Step 1, the function receives the pointer n. Step 2, it uses the asterisk to dereference n, meaning it just follows the sticky note's directions. And step 3, it opens the box and assigns the value 1. Boom. The original variable passed by the caller is now changed, all without the function ever needing to hold the physical box itself. Direct, efficient, and clean.
Which brings us to section 5, pointer inception. Welcome to the boss level, Ultimate point 1.
Okay, take a deep breath for this one. Look at that function signature, func ultimate point 1, taking n, which is a triple asterisk int. Yes, you are seeing that correctly.
3 asterisks, a pointer to a pointer to a pointer to an integer. I know, it looks completely absurd at first glance, but don't let it intimidate you. Think of this like a set of Russian nesting dolls. Or actually, scratch that, it's more like a pirate's treasure map, where the first X just marks the spot of a second map, which leads to a third map, which finally leads to the actual treasure chest.
So the crucial takeaway here is this. Deep indirection doesn't change the rules of the game. 3 asterisks just mean 3 consecutive dereferences. We are simply following 3 maps in a row.
And this just brilliantly illustrates the elegance of Go. To change the value at the very bottom of this chain to 1, we just apply the asterisk 3 times in our code. Triple asterisk n equals 1. Follow map 1, follow map 2, follow map 3, open the box, and drop in a 1. The underlying logic we learned with our very first sticky note applies perfectly no matter how deep the rabbit hole goes.
Finally, Section 6, Comparing the Tools. Let's review our toolkit.
Let's pull up this comparison table from our source document to summarize the whole session. DivMod uses separate pointers for its output, requiring 1 level of indirection. Ultimate DivMod is our renovation expert, overriding the inputs directly in place. Point 1 is our simple remote control, overriding a single input at level 1 indirection. And Ultimate Point 1 is our inception tool, overriding deeply at an indirection level of 3. Seeing them all side by side like this really highlights just how versatile pointers are for managing exactly where data lives and how it's altered.
And here is the absolute proof that our analogies translate into real working Go code. Check out the example usage in the main function. When we print out the results of 13 divided by 2, DivMod neatly places the 6 and the 1 into our separate variables. Ultimate DivMod brilliantly overwrites the UA and UB variables directly, turning 13 and 2 into 6 and 1. And our point 1 and ultimate point 1 functions, they successfully change their target variables to 1 even when navigating through that crazy maze of triple pointers using the ampersand we discussed to write down the addresses on our sticky notes. It just works flawlessly.
We have definitely covered a lot of ground today, moving from the simplest sticky note analogy all the way up to triple pointer inception. Memory manipulation is no longer this invisible, scary thing. You know exactly how to draw the map. So I'll leave you with this question. Now that you have this incredibly powerful tool in your belt, how are you going to use these sticky notes to write cleaner, faster, and more efficient Go code in your own projects? Thank you so much for joining me on this explainer. Keep practicing, and I'll see you next time.